Hello and welcome. In this video we will look at the Modbus server link manipulation feature, available with the 2022.1 release of Typhoon HIL Control Center, which allows for testing how your control system behaves in response to communication network faults, such as those caused by cyber attacks or network infrastructure problems. The Modbus device component, present in the Typhoon HIL toolchain, emulates a real Modbus server in the HIL device. This component is built to emulate the real conditions of a Modbus network, but until now, there was no possibility to simulate communication network faults. Simulating network faults is important since in real-world applications many issues can cause latency or connection loss in the transmission which are beyond the control of a system operator. A few common causes include long network wiring, gateways, wireless and wired routers, hacker attacks, denial of service attacks, nodes faults, physically broken connections, and still many others. Control systems for real-world devices are expected to perform safely even under these conditions, which normally can only be validated by field testing prototypes. That is why with this new feature we add the option to simulate message delay and connection loss in the Modbus server component. In order to show how to set up these faults and how they work, we will use the example model Modbus TCP client implementation in HIL SCADA from the Example Explorer. This example demonstrates control of a grid-connected energy storage. HIL SCADA is used as a Modbus TCP client and communicates with the battery's Modbus server in the model. Let's open the Modbus subsystem, which contains the Modbus server component, and open the Modbus device properties as shown here. Go to the Faults tab and you can see that there are two options, message delay and connection loss. For this demo we will provide inputs from HIL SCADA, although it is also possible to stimulate the model with signal processing variables by selecting here. Let's select a free IP address for the Modbus server and put it in the model initialization panel as shown here. With this we make sure we won't have problems communicating with the Modbus client in the SCADA. After that simple procedure, let's compile the model and open the SCADA panel. The SCADA panel consists of three subpanels. The left subpanel is responsible for controlling the battery inverter directly from SCADA commands. The right subpanel is responsible for controlling the battery inverter remotely from the Modbus client that is running in the PC. The bottom subpanel lets you select how to control the battery inverter, from SCADA or Modbus requests. In order to test some of the faults we will add the connection loss and message delay SCADA input as text inputs, as shown here. Before starting the simulation, it is important to put the right IP address of the Modbus server in the initialization panel, so that the Modbus client can reach it. Now, let's start the simulation. We can see that the inverter is turned off and we have no voltage in the terminal output on the inverter. Let's switch the control to Modbus by checking the Control with Modbus option here. Now you can control the model from Modbus requests. Let's turn the inverter on by checking this box. Now you can see the terminal voltage increases and measurements are updated every second in the SCADA Modbus client subpanel. In order to simulate the connection loss fault, let's change the status of the connection loss input to 1. Now you can see we lost communication with the Modbus server, the measurements are not being updated and we cannot control the inverter directly from here. Only after we change the connection loss status to 0 can we communicate with the Modbus server again and regain control of the model. Let's try with the message delay fault now. To do that, we will choose an arbitrary delay value. This lets us represent situations which could be caused by a hacker attack in the network or a malfunction in network infrastructure. Let's choose 1 second as a value for the delay. After that you should note that the measurements on the SCADA Modbus client subpanel takes longer updated. This is caused by the delay inserted from the message delay options. Although this stimulation was performed from SCADA inputs, which allows you to stimulate the network faults directly, it is also possible to provide an algorithm that performs the same actions, simulating real-world attacks or breaching into the network by using C code at the model level or in SCADA by using Python code, for example. In summary, thanks to this feature, you can now bring communication network and cybersecurity tests into the pre-prototyping phase, helping you save time in developing robust and reliable control systems. Thank you for watching.